The international organizations were involved in carrying out this project. There are almost all geological surveys of Europe involved. There is the metals industry involved. There are many university departments involved in the project, and there are soil science organizations like Altera or NABO involved in the project. And even around the world we have corporations. CSIRO from Australia was working for the project, and getting even further away, the University of Otago in Dunedin is also involved in this project. So it's really international cooperation, as it should be for issues like that. And we started organizing the project. By the end of 2008, beginning of 2009, we had over 4,000 samples collected, about 2,100 from agricultural land, plowed land, and another 2,000 from grazing land, which gives an average density of one site by 2,500 square kilometers. You may say that's a very low density, but I'll show you examples that I think will convince you that it's possible. Let's start with two of the major elements in soils, calcium and silicon, and you see large-scale patterns here on the map. For example, the band of high silicon values in the right map here in northern central Europe, the little high point between Norway and Sweden here, and you see, for example, very high calcium values down there in Spain, and a special signature over all of Scandinavia. What is behind this? Well, as geologists, we of course look first at the geological map, and this is the map of the soil parent materials of Europe. And you see that many of the patterns that you saw in these maps are reflected in the soil parent material map. For example, the special case of Scandinavia, the oldest rock in Europe, crystalline rocks, no carbonates, which are also seen here in the calcium map. Lots of carbonates in Spain, you see it again in the calcium map. And in northern central Europe, this brownish band there of coarse-grained sandy soils, the deposits of the last ice age. So that's what we really see. Let's look at some of the metals, of the heavy metals, because they are probably most interesting in terms of soil quality. And we look here at lead. First thing we see, two maps, two different sample materials, two different sample depths, and yet the maps are more or less the same. Of course, some small differences, but the large patterns are the same. We see the same distribution across Europe. The second important information, we see a major difference in lead concentrations between southern Europe, high concentrations, and northern Europe, much lower concentrations, about a factor of 3 lower lead concentrations in northern Europe. And we see a pattern again that we saw in the parent material map, the border of the last ice age. This is that we have this major shift, which means we are not able to define one background value for Europe. We really need the regional distribution. We need these maps to decide what is good soil quality, for example, in terms of metal concentrations. If we look in more detail at that lead map, we tried that and we went to explain the anomalies. And you see here, we can practically explain all the anomalies, and the majority, about 2/3, are actually linked to mining districts in Europe. Old mines, known mines, there has been mining going on, and we could discuss at length whether this is now contamination or whether the values are high because there are mines, because geochemists set out to find mines via geochemical mapping, and you would find them here. We have, of course, also we see contamination, quite a few things. If you look at London, you see the impact of a major city. Paris, you see as well, Rotterdam, you see, Bergen in Norway, Lisbon, but not so many other cities. So obviously, the real contamination is at a more local scale than what we see here. We also have some unexplained anomalies, and as an exploration geochemist, you would probably go there and look what that might mean, because it might be an undetected mineral deposit. Interesting may be the anomaly number 22. We couldn't explain it. Geologically, there should be. There's a surprising anomaly just here where we are today, in Italy, at the Roman volcanic province. And it took us quite some time to understand that. It's actually a zircon bound in glass shards in the volcanic materials, in the tuffs. And you see the impact of the volcanic eruption at the European scale going over to Croatia. So some 100 kilometers, And just to remind you what we have to expect in terms of emission if a volcano blows up, I put up some figures here from Pinatubo, which are known, and these are the amounts of metals and lava that comes out of a volcano, and this is actually what we see in the map as the impact of such an eruption. We were looking at copper and zinc, of course, as well, and here the interesting thing are maybe not the high values. If we look at the high values, copper in Europe, again, we had at the beginning some difficulties explaining them. It turned out that most of the highest values are actually in vineyards. So vineyard soil, and that was the closest what we got in terms of agricultural impact at the European scale. High copper in vineyards. More interesting in this map may be the blue areas. If we go to multivariate data analysis, then we see this popping up. Do we see evidence of other anthropogenic impacts? The strongest evidence, to our big surprise, was really the copper in the vineyard soils. We didn't expect that. We were expecting that agriculture will have a very major impact. And yet again, we have to go to the mobile metal ion extraction, and we suddenly see the agricultural impact. For example, high cadmium values over all of Central Europe. Input via fertilizers, just as Luca Montanarella was mentioning a few minutes ago. What levels do we see? Well, we managed to map the background. Obviously, the levels are surprisingly low. Element deficiency, yes, you heard that. Copper, zinc, selenium, quite a few elements, and quite many samples, more than 10% usually, potentially deficient. Differences between European countries, very large, up to a factor of 100. The median concentration differs between European countries. That is quite a difficult situation for legislation. How do you define a background level or a threshold level if you are looking at a factor 100 difference for the median concentration in the different European countries? Overall a factor 6 difference, but up to a factor of 100. Geology and climate reflected. I think we saw that, of course, as a geologist. I'm very glad that I see geology reflected. We were surprised to see such a major influence of climate. In the end, it's of course clear it's soil weathering. Again, back to geology. Is European agricultural soil of good chemical quality? At the scale of our survey, yes. But if we go to a different scale, if we look in much more detail, in many cases, no. You saw this big green imprint there in the Berlin mercury card. So all of Berlin really enhanced mercury levels. And in the surroundings, locally very high levels that are toxic. So, the geological surveys do such projects since over 50 years. The first regional scale mapping of a whole country was in the early 1950s in Canada actually. In Europe the story goes back to Finland, the Finnish Soil Atlas 1992, the first low density atlas, and then a lot of further atlases until we finally come to the two GEMAS books which are now available with today, and it's really a pleasure to launch these here at the FAO World Soil Day. With that, I want to end my presentation. It's of course only a very short glimpse at a very exciting data set. The data set comes with the book. There's a DVD in the back of the book, and there's a complete data set. You can just take it and play with it and do your own maps and disagree with everything I have said. Thank you very much.
Thank you for that presentation, and congratulations on the launch.